All right, so we established in last video that for 5 coordinate systems, you can have trigonal, bipyramidal, or square pyramidal uh, coordination geometries, but because these geometries interconvert very rapidly, you don't usually have isolatable isomers. For octahedral, that's not the case. There's not another low energy geometry that you can access that then will interconvert positions on the octahedron. And so you have a very rich diversity of isomers that can form. And it's quite interesting and I think quite fun to look at all the different cases that can exist. So we can start off thinking about, all right, obviously if you have 6 of the same ligands in the octahedron, there's only one way you can have that. But same thing is true if you have 5 of the same ligands and a second of a new ligand. So you can see like it doesn't matter where this B site is, these are all equivalent. I can get from this structure to this structure just by rotating the octahedron down 90 degrees. So that'll take this pink and move it to this pink spot here, and all the blues would move correspondingly. So there's no isomers when you're this Ma5B type of form. However, if you go to a Ma4B2 type of form, that means 4 ligands are one type and 2 of the ligands are another type, then you can have 2 different isomers. You can have a cis isomer and a trans isomer. And this is defined by how your B-type ligands, your 2 ligands that are identical, are related in space. So if they're cis to one another, you can draw it like this, or you can draw it like this. Those are equivalent. But if they're trans to one another, like here or like here, that's a new isomer. New isomer means, you know, different type of physical properties, different types of reactivities, etc. So 2 isomers for Ma4B2, we call them cis and trans just by looking at where the B's are. You can keep going to different permutations here. What if you have 3 ligands of one type and 3 ligands of another type? We call that Ma3B3. Those also, it turns out, have 2 different isomers. These are called the facial isomer, abbreviated FAC, FAC, and the meridional isomer, abbreviated MER. How does this work? Why are they named this way? Well, this is called the facial isomer because all of these are on the same face, right? So you can see that there, you can draw a triangle, basically, between these B's, okay? And you could also draw a triangle in the back here between these A's. So, you know, an octahedron, remember, is called an octahedron because there's 8 faces. There's 8 triangles make up the octahedron, right? You can kind of see there's one here, one there, one there, one in the back. So 4, and then so 4 on the top and the same 4 on the bottom, giving you 8. People get confused by that a lot of times because you think, well, an octahedron shouldn't that have something to do with 8, so it should have 8 ligands. No, you have 6 ligands, but in 3-dimensional space, they give rise to 8 different 2-dimensional faces. Octahedron means faces. So this is the facial isomer because you have the same isomers on the same face. This is called the meridional isomer. And the reason why is because they're oriented differently. And so the best way to think about this is think about this as sort of a sphere now. And these are kind of making an arc right there, right? And so that's kind of nice way of thinking about it. Meridian, you know, like prime meridian on a globe, right? Meridian is something that cuts through a globe like that. So it makes these sort of arcs. So that's the way that I remember the difference between the facial and meridional isomers. So yeah, for the Ma4B2, we established that there's a cis and a trans isomer. You can try to make something more complicated, like if you go to Ma4BC. So this would be 4 ligands that are the same type, and then a second ligand that's a different type, and a third ligand that's a different type, right? Turns out there's only cis and trans isomers here too. It's no more complicated than this Ma4B2 case. And the reason why is because this is just defined by how your B and C's are related to one another. If they're cis, it's going to look like one of these drawings, perhaps, or if you're trans, it could be one of these drawings. These are equivalent. So there's only 2 isomers, and we track it by looking at whether or not B and C are cis or trans to one another. If B and C happen to be the same, then you collapse to this top case, right, where you're Ma4B2 isomers. So there's a lot of different permutations we didn't go over. where you can get increasingly levels of complexity. But let's just jump for the sake of time here to the most complicated case, and kind of the most interesting, I suppose, which is when you have 6 unique ligands, okay? So we could call this M, A, B, C, D, E, F, all right? It turns out here there's 15 isomers. So how are you gonna, generate these or keep track of all these? If you go systematically through this, it's not too bad. And I can explain to you fairly straightforwardly why there are 15 isomers, okay? And here it goes. We're going to be looking at cis and trans relationships. I'm going to just focus on trans to keep track of it. You can use either. Okay, so let's say we take this first example, okay, where we have, this one is trans AF, right? A and F are trans to one another. Okay, so if I say, hey, A and F have to be trans to one another in the ones that I'm evaluating, then what do I have left? I have a square planar complex. And we know from our previous discussion that if you have a square planar complex, okay, with 4 different ligands, M, A, B, C, and D, that there's 3 different isomers, okay? So what that means is that I'm going to have 3 different isomers for all the cases that there's AF, right, trans to one another. So let's look here. Where are the other AFs that are trans to one another? I didn't do a good job putting these in any sort of order, but let's see here. AF trans to one another. Here's one. A and F are trans to one another. Okay, so that means this square planar part must be different than the square planar part. Within the square planar part, are they different? D is trans to E. Yeah, and here B is trans to E. So the one that we're missing is C is trans to E. That's the last one. Okay, so we're looking for A is trans to F, first of all. Okay, so here it is. A is trans to F, and we said C is trans to E. So again, how I drew it here is like this. So all 3 of these that I've marked up on, A is trans to F. Fine, A is trans to F. Okay, and now we have C is trans to E, D is trans to E, and B is trans to E. Those are the only, so there's 3. For 3 isomers, just because square planar has 3 isomers for 4 different ligands. One A is trans to F. Well, what can A be trans to? Okay, so A trans to F gives 3. Well, A can be trans to E. Okay, A can be trans to D. A can be trans to C, or A can be trans to B. That's it, right? And each of these is going to have 3, right? Basically, so that's 3 times 5, right, is going to be 15. So that's why there's 15 isomers here. Basically, for every atom, for every ligand, you can be trans to 5 different other ligands, because there's 6 total in octahedral. And the square planar kind of equivalent complex that's within that, once you fix your trans, has 3 different isomers. So 5 times 3 is 15. So for an extra credit point, what I would like you to do is tell me how many isomers there are for MA3 for MA3 BCD ligands. Okay, MA3 BCD, and I also want you to tell me which one of those are chiral. Okay, if you look at these, all of these are chiral. Okay, all of these are chiral, all 15. Why are they chiral? What point group are they? They're point group C1. So you have 15 different geometric isomers, and they're all chiral. So the mirror images of all these are not superimposable. That means if you're able to distinguish between isomers, the enantiomers, you have 15 pairs of 15 pairs of enantiomers. So you have 30 different isomers per pole, because you have a mirror image of all these ones that I wrote right there. So that's pretty cool. Gives you an idea of, just the structural diversity that can exist with octahedral isomers. Many other combinations possible that we didn't talk about. If you have substitutions on chelating ligands, that can give you even more isomers or induce chirality if they're binding in a certain way. And you can imagine, what if you have multi-metal complexes, right? You have two metals now. There's lots of different isomers that can form. Just to briefly talk to you about the chirality that can be induced by the ligands. Consider, for example, these propeller type molecules where you have equivalent bidentate ligands binding on 3 different sites. This is doesn't have a mirror plane, and this is a chiral molecule. Okay, and so you have a right-handed and a left-handed version of this molecule. It's given a certain name. You may see this in the literature, where if the spiral goes away from you and goes in a clockwise direction, it's kind of like a helix. It's given a delta, okay, capital delta, Greek letter. If it's counterclockwise, it's given a capital lambda Greek letter. So how does this work? You can see here, this blue triangle is the kind of top of this molecule, viewed like a propeller. If you rotate this clockwise, this point, these are your binding ligands. So to get to here, you have to go clockwise. You have to go this way. This point has to go that way. That point has to go that way. When you're going, going away from yourself. So it's going like this. The helix is going like that. It's right-handed. So it gets this delta terminology. The opposite way, when you're going counterclockwise, going that way, going back down that way, you're going from here back down that way. That is given the lambda designation. So there's a lot of different ways of naming these chiral systems. It can get pretty complicated. Even these isomers, which are chiral, you have to use the same nomenclature rules, or very similar set of nomenclature rules for naming chiral RNS enantiomers in organic chemistry. That's typically what is used. Again, I'm not a huge nomenclature person. I do want you to be able to identify if you have a chiral molecule or not, if you have a chiral isomer or not, but I'm not going to test you on the nomenclature. I just want you to know, on chiral nomenclature, I just want you to know that it exists.